Today we continue exam preparation and will be part 2, and we will do with a harder one today. We'll start with second. So we want an integral of second of x dx. So that's none of the ones that we know. We do know that tangents become second square, therefore second square can be returned back to when you derive derivative of tangents is a second square. So but therefore returning back could be only from second square to tangents, not from second. So we do know that tangents of x, and first derivative is second square x, but that second square, it's not second, so we can't use that. So what we're gonna do? But there is something, and what it is, it's a trick. It's a trick. So you multiply second and divide, so you multiply and divide the second with the same expression. So you go second of x times, and you multiply by, this one is characteristic, second of x plus tangents of x. Second of x plus tangents of x. You divide with the same. Second of x times tangents of x, and you know nothing will happen when you divide and multiply by the same. So why are we doing that? But soon it will be shown. And dx here. So what we want to do, like, you will do that because you want to apply this substitution. Second of x plus tangents of x is our u. So what's our du? Our du is the first derivative of second. So I go second of x derivative plus, what's the first derivative of tangents? We know that it's second square of x. Oh, that's pretty good, but what's this derivative here? So let's do it. Derivative of second of x by dx. So what's second? Second is 1 over cosinus. 1 over cosinus, and you want the first derivative. So we can do a substitution, because this looks like 1 over something, and that's u on the power minus 1 and x. So we do a substitution. We'll substitute cosine of x with u. And then what we're going to say, what's our du? Oh, we do know that. That's minus sine of x. So what does that become? So this is like the chain rule. This is Yeah, so 1 over u, so u on the power minus 1, that's the whole thing here. First derivative is minus u on the power, so the whole thing minus 2. I shouldn't call it u, should call it v, because this is now the chain rule, the embedded function. So let's say v, that's the whole thing. V is 1 over u of x. U of x is embedded, it's here. So minus that times, and now we have, what did we say? It's the, so that's the derivative of the first one times derivative of the second one, which is the cosine. So that's our v here, and it's our u here. So times the derivative of u, and that's times minus sine of x, and that's minus times minus plus, and that v, our v is on the minus 1, so that's 1 over cosine of x on the power of 2 times sine of x, oh, 1, huh? That's that one there, and that's what that sine, oh, you have one cosine times cosine, sine with the cosine gives a tangents, and you have one cosine left, and 1 over cosine is second, so you get tangents of x times second of x, and that's the final. So let's circle that. That's our derivative of second. Just to be clear, this is our v of x, and this is our u of x. So we're applying the chain rule. So you know how it goes. The first derivative of the outer one times the first derivative of the inner one. So the whole thing was v of u of x, and then the derivative was, you know, but how that goes. It's v prime of x times u prime of x. Okay, let's go down to, up to solving this problem. So what we have, we've done this bit here, so that becomes, let's copy it, the first derivative of second is tangents of x times second of x, and that plus second square of x from here. So let's now delete the below. So what you saw with the chain rule for derivatives and, as you know, substitution for integrals. So that's the guiding principle, the chain rule for derivatives, the substitution for integrals. Okay, we got this du, so now we can go further. So what does this look like? We have a common second here. So second of x we take out, and in the brackets we have tangents of x plus second of x. So if you look now, what you look up there, now look there, and what do you see? That this bit here, our du, is the same as this bit here. See, they're the same. So what that's it, what we want, don't we, to eliminate the numerator. And what does it become? It becomes an integral of, so that up there, du. So our u is the bottom, it's u. So this bit here is u, and the bit above is du. So it's 1 times du. Oh, I've forgotten here that here we've forgotten to put dx, right? Times dx, yeah? Because of the derivative, right? Because derivative dx, derivative by u, derivative by x. So what's this? Oh, that's a natural logarithm, ln, an absolute value of u plus c. And what does that become? Ln absolute value. What's our u? Second x plus tangents x. Second of x plus tangents of x plus c. So it's a good one to remember, the one for future work, it can be useful. Then this second integral is this, is ln of second plus tangents. It's a good one to remember. And the good thing here is this substitution to remember. Let's do a bit of derivatives. Let's now do it the contra way. Let's do a derivative of ln of second plus tangents and prove that's the second. Let's do it the reverse way. I'll make some room. So what we want to do with this is to find the first derivative of dx of ln of secant of x plus tangents of x. Now we can delete the bottom. So we want to prove that is equal to secant of x. So let's do the derivative. So again, the chain rule. The outer one, the outer function is ln of something. So say that's v, and now embedded into v is u. So of x, v of u, x, but this v is of u of x. So v of u of x, and that's embedded v of u of x, u of x. So what we get, let's do that. So the first derivative of ln, so let's derive that. That becomes 1 over the other function, whatever that is, that's secant of x plus tangents of x. That's the first bit. And then that multiplied by, it's the first derivative of u of x, that's the first derivative of secant of x. So secant of x, the first derivative, times the first derivative of tangents of x, we do know that, that's secant square of x. Alright, so what's the first derivative of secant? So we don't have that in our table, so we can derive it. So what's secant? Secant is secant of x. Secant is 1 over cosine of x. So if you go first derivative, so again, the cosine on the power minus 1. So what's that? That's cosine of x on the power of minus 1. So like, again, we have an embedded function, u on the minus 1 times, so chain rule, that's minus u, which is cosine of x on the power of minus 2 times the cosine, its first derivative is minus sine of x. So sine times negative positive, so we get left with sine of x over cosine square of x. And sine over cosine is tangents, so we have tangents of x times 1 over cosine of x, and then bring us to tangents of x times secant of x. So let's do that. So what we have there, for the first derivative of secant, we've got tangents of x times secant of x, and that's there, and that's times second square of x and that's divided by second of x plus tangents of x sorry, here is the plus sign, so we have that plus here. So what we're getting is not this, it's this plus second of x separate. So that plus second square of x yeah, and this is the whole lot, yeah. And just continue there, plus that, because that plus sign is from here, plus plus, that's that. So what we got here, second is a common one, second of x, we have tangents of x plus second of x and divided by second of x plus tangents of x, and because we have the multiplication here we can cross out these two and what's left is second of x. So we prove that second of x is second of x here. So the first derivative of ln of second of x plus tangents of x is second of x, or vice versa. You need to remember vice versa. Vice versa, that integral of second of x is ln of second of x plus tangents of x. Vice versa. So the equation is, so the integral is 0 to pi third tangent square of x times second square of x dx. U is the substitution for tangents x because the du will be second square of x. Therefore, we will use second square of x dx, replace b with du. Therefore, du second square of x dx. So the integral becomes, we'll change these boundaries because of x and u in a moment. Just finish it now. U squared du. So when x is 0, then tangents of 0 is sine of 0, which is 0, so u becomes 0. So when x is 0, u is 0. Okay, so should have said x. X is 0, u is 0. And now when x is pi third, that's 60 degrees, that's square root of 3 divided by 2 divided by 1/2. So we know that those two numbers we need to remember, that's the only ones. For 60 degrees, square root of 3 divided by 2, and for the other one 1/2. So whichever is bigger, sine or cosine, the bigger one gets square root of 3 by 2. and the other one gets 1/2. So in this case, sign is bigger, gets square root of 3 by 2. So square root of 3, and there, square root of 3. That's it. Now that becomes 1/3 of, and then u on the power 3, and the boundaries are 0 to square root of 3. So put the 0 and square root of 3. So square root of 3 on the power 3, u on the third, and square root of 3 is 3 on 1/2, so that's u is then on square root of 3 on 3 is 3/2. Um, 3 is 3/2. So square root of 3 is 1/2, so 3 on 1/2 is square root of 3. Square root of 3 on 3 is 3 on 1/2. 1/3 is 3 on -1. So times 3 on 1 -1, and -1 is 2 divided by 2, so 3/2 minus 2/2 is 1/2. So it's square root of 3. And that should be our result. And that's what we started from. And that's all.